So, when we put a spoon into some water, why does it look like it's been snapped in two from the side? Okay folks, so let's have a look at a pencil. Does it do the same? Yes. So what is happening there? What causes the pencil to look like it's been snapped in two? I'll just pull it out to prove to you that it's a solid pencil. There it is. And if I put it back in here, there we go. What's happening there? Can you explain it? Okay folks, so I have a infrared temperature probe here. So when I press the button, it actually tells me the temperature of objects. Now, this video isn't about this today, but it's quite a cool little gadget, so maybe I'll make a video about this another time. But the reason I'm using it is it has a laser, so if I point this at the table, hopefully you can see that. So the reason I'm using the laser is because it gives me a nice beam of light, nice ray there that I can use. And I've set up some paper on my table here, and I've found a nice glass bottle. So that is my setup, and what I'm going to do is show you a little experiment and see if I can get you to think about why the light moves when I introduce this into the path of the beam. Okay guys, I have turned on the laser. I've used a bit of tape to keep the button down, and you can see here, if I put my finger there, that the laser beam is going all the way to our piece of paper here, and I can promise you it's making a nice straight line. So if I was to put a ruler on there, it's nice and straight like that. So what I'm now going to do is, using my trusty pen here, I will mark a little line on my backing here. So that's the original dot. Now if I just introduce this into the path of the beam here, there we go, it has now moved. So my new dot is here. I haven't moved the light is still travelling in a straight line, but why, when it goes through this glass, if I do that again, does it jump from here to here? What happens? Can you work it out? Okay, so let's have a look at the science behind it. So we'll look at refraction through a glass block. So I don't have a glass block here, and I suspect that you won't have a glass block at home either. So you're more than welcome to use something like this, a glass bottle. That will work equally as well. Try different shapes and see what happens. But I can tell you that refraction is when light bends as it crosses a boundary. So this would be a boundary here, this block of glass. So the light comes in from my laser beam, from my laser pointer here, and as it enters the block of glass, the light is slowed down, and that causes it to bend here, or change its angle. And then as it escapes, it speeds up again and comes out in this direction. Now, let me explain that in a bit more detail for you. Okay, so let's have a look at some explanation for this. So I've got a couple of explanations for you, but the first thing I will do is just draw some soldiers. Now imagine that you are looking down from above, so you're in a drone or a helicopter looking down, and these are the tops. You can see the heads of some soldiers, and they're walking this way. Now, they're all walking in a straight line, so they're all marching along in a straight line, as soldiers do, but they approach a rather boggy field, and it's all muddy and sticky and horrible. So here's the field. So as the soldiers come along, this chap here is going to hit the field first, isn't he? And he's going to slow down before the rest of them, because he's going, oh, it's all muddy, I can't move very easily here. Then this chap, and so on, along the line. Now, because this guy is slowed down first of all, he starts to go off course a little bit, and he goes down this way at slower speed, and the same with this person, and so on. So as the light enters this muddy field, or as these soldiers enter this muddy field, they're knocked off course a bit, if you like, but they're slowed down. Now, we don't normally see this because light travels very, very quickly, and it's normally a very thin beam of light that we use for this explanation. But if you imagine this light was a bit thicker, so if I turn this over, there we are. So if I use the same explanation, our soldiers are coming along here, and they are going to hit this muddy field or block of glass at a different time. So if I, instead of using a thin beam of light, draw it a bit thicker, hopefully this will make sense. So here is our muddy field again, and here are some soldiers moving. So it's a beam of light and it's a block of glass, but if I use the analogy of our soldiers, if I make this a lot thicker, it should help to explain. So here's a group of soldiers going along like this. So there's 3 of them. When they get here, this person's slowed down first of all, so he's going to go a lot slower. This one's, and these 2 are still moving quite quickly. But as this chap here enters the field, he's slowed right down because it's all, it's all muddy and horrible. This person here is just getting to the edge, and this one's absolutely fine because he's still in open country. This one's still going at the same speed. This chap here has just entered, so he gets slowed down. And then the same with this one. This isn't completely accurate how I'm drawing it. But can you see that this one here entered the field at the end, so he's slowed down last. So they go through the field, they're still marching, but they're struggling away in the mud. And then the same is true when they come out of the field. So this person here entered the field first, so that means he'll escape the field first, and then he'll speed up again. So he'll speed up and his course will change. Then it'll be this person, they'll speed up, and this person. And then eventually they'll regain their original direction, if you like, original sort of angle, but they've been slowed down by the field in between. So that's what's happening here. So we've got our angle of incidence, it's called, up here. So that's where the light enters the block, or the field, if you like. And then we have our angle of refraction, and that is the angle that we measure to see how much it has been refracted. We always measure against the normal, so we always draw a line like this, 90 degrees to our field or block, and we always measure this angle here relative to the normal. So you've got angle of incidence, this one here, and then the angle of refraction therefore is this angle in here in the field. So we use our protractor to measure that. So that is why when you look at a glass with a spoon in it, it looks like the spoon is broken in 2 or bent somehow, but it's actually just the light being slowed down by the thick liquid, which is water. So there we go. So my last experiment here is if you put a coin into a glass, it doesn't seem to be quite where you think it is. Now the reason for this is that when you look at the glass, your eye is almost tricked a little bit into thinking that the coin is over here, when in actual fact it's here. So the light travels through the water and it starts to slow down as it hits the water because the water is more dense. This makes the light bend and tricks you into thinking that the coin is closer than it actually is. Now you might have experienced this if you ever go swimming and you have a weight that you throw into the pool, one of those rubber bricks, and you swim down to go and get it, and when you put your hand out to grab the brick, it's not where you think it is, and that is an effect of water slowing down light. So have a go at some of these experiments at home. Just put a pencil into some water and have a look at the side and see what happens, and also try filling up something a bit bigger than a small cup here, a small glass, with some water, and put something in the bottom of it and see if you think it looks like it's not where it should be. When you put your finger in, is it where you expect it to be? So there we go. There's some STEM experiments for you that you can try at home with light.